Hey guys, this is Academia On Demand and I'm Josh Myers and I am finally bringing you some application question videos, which basically means that instead of teaching you stuff, I am going to be going through questions, because the best way sometimes to learn the stuff that we need to know in this nice institution we call school is to actually do questions and model out these questions so that you can see how we would apply the things that we've learned in order to make our teachers very, very happy. Okay, so the question that I am going to write out for you guys today is and is very, very generic, and I will run through exactly the best way to answer these questions, but use bonding theories. Use bonding theories in order to IO2 explain the similar bonding behaviors, of oxygen and sulfur. And the second thing that I would like to run through with everyone is the idea of use bonding theories in order to explain bonding. Oops, I am using big letters. Why am I doing that? That is for the big part of the question up there. So erase. Sorry everyone, I'm going to get into this video eventually. Bonding in, and now we have a second set, so now we're going to use dashes again. Further over to the right, we are going to explain the bonding of phosphorus pentachloride, so PCl5 pentachloride, and we will also be explaining xenon tetrafluoride, and we will see that's pretty interesting. And then finally we will be explaining the delocalization in O3, and maybe if we're lucky we might do a bonus. We'll do a bonus of this organic molecule, very, very famous, called benzene, which is C6H6. Okay, but the first thing on the agenda, before we can do any of this stuff, is we gotta answer the first question. This first question is very, very systematic, and the best way to start this question out is by looking to the Lewis theory in order to display the bonding of oxygen and sulfur in example molecules. So a very good way of explaining this question is to give two example molecules that it just so happens have very similar molecular geometries, and thus the bonding in them is very similar. So two examples involving oxygen and sulfur. Okay, so the first one that comes to mind, the most famous molecule that involves oxygen, it is the one that keeps us all alive. It is H2O. And it just so happens that this molecule, this idea of hydrogen being bonded to two things, by the way, both of these elements, oxygen and sulfur, are group 6 elements. And it just so happens that this idea of hydrogen bonding to oxygen, just as I said, can also be replicated with sulfur in the form of H2S. And so how can we use this relationship between them both being group 6, and then in these examples explain how their bonding behaviors are similar? Okay, so we are going to turn to our Lewis theory, and we are going to say, first, before we explain more specifically using hybridization, what do these molecules look like? So that way when we start using hybridization, we can refer directly to a diagram. That is why the Lewis structure skill, though inaccurate, is still extremely important from a practical standpoint, from a pragmatic standpoint. So our H2O has six electrons here, 2 electrons with the 2 hydrogens. That is 8 electrons. 8 electrons. We know O is the central because it's the singular atom in the molecule. And now we've got 2 hydrogens bonded to it. 2 hydrogens bonded to it. And then, as we know, the hydrogens are energetically stable. They only need 2 electrons. And then the remaining 4 electrons are bonded as lone pairs on the oxygen. And so this creates a molecular structure. Now we're going to erase these bonds because they are, as we know, shifted downwards due to the relatively greater repulsion of these lone paired electrons. Shifted down so that this is H and H. And so this same molecular geometry model that we have over here can actually be applied directly in order to show how it is bonded, how sulfur and hydrogen are bonded over here. Because as we know, they are both group 6, so therefore they both have the same number of valence electrons. Same number of valence electrons. And because of this, they will bond in this setup in which there are both 2 hydrogens, and simply the only thing that is switched is the sulfur and the oxygen. It will bond in the same way. So we will have the 2 lone pairs and then a hydrogen and a hydrogen, and everyone is happy with 8 electrons or 2 electrons with the hydrogen. Okay, so we've shown this. This is the basic outline, is the basic fundamentals, what in every single bonding question will need to be shown in order to please our teachers and have them jump up and down and give us great marks. These are the basic outlines. But what will really get you the marks and really show your understanding of exactly how bonding theories relate to each other and how they relate to this question is to do some hybridization. And we know whenever we're doing hybridization, we need to display the valence energy orbitals in order to display the electron promotion, because we know we need in hybridization, we need to display electron promotion, and we need to all write this down. I know that you're sitting in front of your computer with a paper right now, and you need to write these down. These are very important when explaining things using hybridization. So electron promotion, and then the display of, so creation of hybrid orbitals, hybrids, let's just call them hybrids, but we know they are hybrid orbitals, and hybrid orbitals are orbitals that are ready to bond, or at least ready to influence molecular geometry through repulsion, because as we know, these are sigma bonds, or at least lone pairs that may lie in hybrid orbitals that may influence molecular geometry. So influence geometry. And this is something we got to keep in mind here when we're talking about sigma and pi bonds later, and that is the next step. So the creation of the hybrids. And then finally, to label based on the hybridization. So based on hybridization, and what I mean by this is whether it's sp2 or sp3, which is all determined by the number of areas of electron density that influence molecular geometry. So as we know in this example, it's sp3 because we got 1, 2, 3, 4 areas of electron density that influence the molecular geometry. So based on the hybridization, now based on this idea of sp2, sp3, what we just discussed, where are there sigma bonds Or where are their pi bonds? And I'll try to draw my best pi symbol again. Alright, I tried. Okay, so given this list, we need to run through this list very systematically. How are we going to explain this shenanigan that's happening here? Well, okay, same number of valence electrons. Let's keep this. This is a good point. I want to make sure that stays there. Okay. So the easiest way to discover how the electron promotion happens is to draw out the box diagram for the orbitals, for the valence orbitals of sulfur and oxygen. So here we can actually just say S and then P, because as we know, in oxygen it would be 2s and 2p, whereas in sulfur it would be 3s and 3p, because they are simply an energy level removed from one another because they are in the same group in the periodic table. And now we are seeing why I did that very long, tedious second video, maybe third video, one of the beginning ones on the periodic table, because it just, this idea of language when applied to the organization of the elements could not become more important than it is right now. Okay, so oxygen, and we know it has 1, 2, 3, 4. It has 4 electrons. It's a 3p4 element, and that is its 2p4, 3p4, sorry, element. That is its valence electron shell. So, as we know in hybridization, it is going to promote this electron right here, and it is going to put it right here with opposite spin to this one. And so this will create the hybrid orbital of sp3, which is 4 orbitals of equal energy combination, overlapping, as we saw in the last video, this word is amazingly important, overlapping of these s and p orbitals in the creation of the hybrid orbital. And we will see this word overlapping again, or blending or mixing is another way that we can say, we can communicate this idea of combining sort of thing. Okay, so these are the P's, and this is the final P. And so what we have here is an arrangement of electrons in this sp3 hybrid orbital, in which all orbitals are of the same energy, same shape, they are all the same, and we are simply communicating how do these relate to here. Because we know, because they are both group 6, they will both have this hybrid orbital that is the exact same. And here we could almost, if we were trying to be very short and cute, we could almost say that this is the ending of the question, because it asks us to explain explain the similar bonding behaviors of oxygen and sulfur. Well, we could simply end with, well, in their hybridized state in this molecule, they have the same arrangement of their hybrid orbital, and this is due to the fact they have the same number of valence electrons. We could simply end it here, but one of the biggest ways, the easiest ways, the most compelling ways to show your understanding of any sort of theory in science is to relate it back to the initial diagram, the picture. So how does this relate to the picture? So we know that in both of these molecules, 2 hydrogens are bonded to the central sulfur and oxygen. So now we can say, let's attach, because we know that hydrogen has 1 electron in its 1s orbital, we can bond these 2 together. And then same thing here, because there's another hydrogen, 1s, 1 electron, we can bond these 2 together. And so that is where these two bonds, let's make sure to box them up, make them important. These bonds are represented in the hybrid orbital. But then we still have these two orbitals that influence the molecular geometry, even though they are non-bonded orbitals. So non-bonded, NB. And so what they appear as are lone pairs. And that is why in both of these molecules, this O and S both have two lone pairs attached. It isn't just because, as I discussed it, this is why the Lewis theory is not accurate, because it's not as though there's simply a pool of electrons and we've just decided that because the hydrogens are okay here, now we're putting these lone pairs up here, and just happens to work out that all of the oxygen, sulfur, everything is all energetically stable. No. In hybridization, because of the presence of two hybrid orbitals that are already full, they by design are already lone pairs. And this is something that I just really wanted to clarify in this video to really display the understanding of hybridization theory in general. Okay, so we've really hit hard on that question. We're almost 15 minutes into the video, I think. 16, actually, now that I'm checking. And I will probably go through two more examples of the molecules that I was planning on showing. And then I will maybe leave for another video the idea of the delocalization, because that will be very hairy, very not nice to explain, and I will bend my brain corners and corners and corners around this earth to explain. Okay, so the next molecule that we were going to look at is the phosphorus pentachloride molecule, PCl5. And so, as we know, before we even begin to draw this molecule, is that this is an extended octet molecule, because we know whenever any central atom, here phosphorus, is bonded to more than 4 things, more than 4 atoms, it is clearly an extended octet, which means that it takes advantage of the d orbital. Takes advantage of empty d orbital. Empty d orbital, because as we know, the s and p orbitals only have the capacity to hold 8 electrons. And here, if we have 5 bonds, clearly there are at least 10 electrons around this central phosphorus. And so clearly there must be electrons that are going somewhere else. But how does this happen? And this is where we will get super compelling, and we will move beyond previous videos where we have discussed this idea of extended octet. Again, I keep going back to all these ideas because they are just so important, and the best way to learn is to reiterate and keep going over the central themes. And so, as we know, we want to draw the Lewis structure. That's the best way to begin this sort of explanation of how bonding theories are used in order to explain the bonding of PCl5. Okay, so we know that phosphorus is the central, and we know if we count the number of electrons available for bonding, we've got our 7 in chlorine times 5. 7 times 5 is 35, plus the 5 in phosphorus, there are 40 electrons. 40 electrons. 40 electrons. Okay, so there are 40 electrons, and actually I'm going to move this P down because it's gonna start hitting that 40. Okay, so P right here. And so we know that there are 5 chlorines that surround this central phosphorus. 5 chlorines. Let's draw them roughly evenly apart in our 2D space board. 2D space. And we know obviously that this is 3D, but I will not get into that nonsense. I think that it is great for understanding, but not great for when you initially learn something. Okay, so this PCl5. And so if we just picture this chlorine, the chlorine atom, it wants 1 electron to complete this outer orbital. And so if we draw out its box diagram, because now whenever we're talking about hybridization, we're talking box diagrams. we've got these electrons, and then just keep going here. I think we will end with this. And this is, it's 2p orbital. And as we know, there are 2 completely full orbitals and then 1 half-filled orbital. And that when it hybridizes, because even though we've mostly been talking about hybridization in terms of the middle atom, in fact, all of the atoms around the phosphorus do perform hybridization. And so when the hybridization happens, this s electron is promoted to this position, and really we still end up with the same structure. This does not change very much in terms of our perspective of how many orbitals are open. What it simply changes is now this chlorine is sp3. sp3, and this seems odd, but it will make sense in a second, hopefully. Okay. Oh no, this is bad boxes. Okay. Try to make them better. Alright, so, and this is our S, and it is now half full. So it is ready to bond. It is ready to accept a half-filled orbital electron and complete this orbital. So then up, down, finally up, down. Okay, so this is clear demonstration, understanding that chlorine needs 1 electron to complete its outer orbital. And so because we know that this hybridization happens, we can automatically draw in these lone pairs, because all 3 of these hybrid orbitals in this sp3 are full. So they represent non-bonding pairs, which are these things around this chlorine. And as we know, and we can do this to all of the chlorines. Oh shoot. Oh no, okay. Alright, chlorine. I'm saying chlorine. Okay, so you can do that to all of the chlorines, but what is actually really surprising is that they are hybrid orbitals, and so that means that they do influence the molecular geometry. It would seem as though they would influence the molecular geometry. But the exception to this idea of them influencing molecular geometry is, sure, they influence the bonding around this chlorine atom, but they do not influence the bonding around the phosphorus atom, because they are not connected to the phosphorus atom. And this is a definite distinction. Another thing I wanted to bring up in this video is that the hybrid orbitals only influence molecular geometry if they are bonded to, they are non-surrounding atoms. So if they are bonded to other things, if they are a central atom in some sort of bond sequence, so like and when I say bond sequence, if there were to be a bond here that was C, and if there was a hydrogen attached here, and of course this would take on a positive charge, because if you added this hydrogen, you'd have to add an H+, but let's not get into that right now. If you added a hydrogen, what would happen here actually is you would have a situation where if this was bonded here, this lone pair would come up here, and this would become a bent tetrahedral, bent tetrahedral. And this is super interesting because it actually would have the same molecular geometry as water, as what we saw in the last example. And so this really shows that these orbitals are hybridized. It's just that this chlorine is a atom surrounding the central atom, and so therefore the lone pairs attached to it do not influence the overall molecular geometry. So just trying to make things as clear as possible for all of you out there trying to go through all this tough stuff. You're being science warriors. Okay, so move on with this example. So we know they all have lone pairs, and so now we just need to find now what the hybridization of the phosphorus is, because then once we have that, we can start to pair up these half-empty orbitals of the chlorine with the hybridized electrons of the phosphorus. And so we know that phosphorus has the valence electron configuration box diagram of 3s and it's full, and then 3p, shoot, I am not thinking right now. It is the second night in a row where I've had 5 hours of sleep, and I really need to pick up my game with those habits before I go to university in like 4 days. This is going to be a big step in my life. So we've got our half-filled orbitals in the 3p sublevels. So this electron promotion occurs. And this electron comes in here. It comes in here. And so as we would just automatically assume, this would become an sp3. It would become an sp3. And it would have the configuration. Of this blending. It would have this, and then this full orbital, and then these three half-filled. And so we would think, oh, that's nuts. It can only bond to 3 things. These are 5 things. How does this happen? This is insane. But then we remember the empty d orbitals. And then it starts to make sense to everyone. And this theory really starts to hit home. And this is really how hybridization is the very, very specific, very, very educated, most correct theory in its explanation of how these things happen. And this is really where we start to look a bit deeper. And so if we draw out the 3d orbital, the 3d, and as we know, the d sublevel has 5 component orbitals. 5 component orbitals. Oh no. And as we know, because it's only phosphorus, because we know that no electrons have been added until we get to scandium, which is, I believe, is atomic number 21, we do not have any electrons there. But what can happen here, and what does happen here, in fact, is that this electron promotion doesn't go to the 3p orbital. What actually happens is that this electron goes to one of the 3d orbitals rather than the 3p. And now we have, if we take all of these and we put them all together in this big mess of stuff here, if we mix all of these together, mix all of them in space, we get our excellent 3p, 3sp, 3d, 3sp3, because it's in the 3rd energy level, we can really get rid of that, sp3d hybridization. And it looks like this, with its 5 orbitals, because it's got its s, half full, p's, half full, and then it's d, half full. And so this fits exactly our model of the way we're looking at this molecule in the Lewis structure. And because it's got the 5 half-filled orbitals, so 5 orbitals that, if filled in with this s electron, can form bonding pairs. And that's exactly what happens. That is exactly how this process takes place. 5 bonds. And now let's count the number of electrons to ensure that we've done everything right, because this is always the checking mechanism, is counting that the picture has the number of electrons that it is supposed to have when we look at the valence electrons of its component atoms, so phosphorus and chlorine. So we've got our six electrons that are lone pairs are on each chlorine. That is 6 times 5 chlorines. There's 30 electrons plus 2 plus 2 plus 2 plus 2 plus 3, and we are good. 40 electrons. And that is exactly how you would explain a question like that. Be very thorough. 40 electrons, and I like check marks. Okay, check marks. And so this molecular geometry would be called trigonal. I'm not going to say trigonal planar. I've written that enough times. Trigonal bipyramidal. Bipyramidal. Trigonal bipyramidal, and that is trigonal pyramidal as we would think in a geometry that's got the 3 bonds and then the 1 lone pair, so sp3 hybridized, but it is a bipyramidal, which makes it this geometry. 5 bonded pairs, no non-bonded pairs on the central atom. Okay, and so where am I at in my timing here? About 31 minutes, wow. Okay, so if I am going to truly finish up this video, because this is already super ridiculously long, I am almost very upset with myself for not keeping track of time here. But if we are going to truly finish up this video, because I know if you're still watching right now, you're a very dedicated learner and you're willing to watch for another couple of minutes. So that final example we were looking at is XeF4. XeF4, and as we know, Xe is a noble gas, which is very unusual to see bonded to anything. See bonded to anything. I'm going to try to go quick here, but here it can actually, using hybridization theory, we can explain very nicely how this bonding, how this idea of xenon bonding can actually happen with relatively small amounts of difficulty. Okay, so if we have our, and we're just going to skip ahead here, if we have our F, because as we know, F and Cl, because we showed PCl5 in the last one, F and Cl are in the exact same group, and so their hybridizations are going to be the same, and so they will each prefer to form 1 bond. But what we're really going to look at is the hybridization of xenon. Because as we know, this molecule, given that xenon has 8 electrons and fluorine has 7, this molecule will have 36 electrons. And so we are going to look at the hybridization of xenon. Okay, so we have xenon and we draw out its box diagram. Okay. Box diagram. Oh no. What is happening? I am losing my mind. Okay. That is its S and its P. And as we know, it's a noble gas, so it's got already stable full outer energy level. But because of how low it is down in the periodic table, it also has access to d orbitals. And these orbitals are going to have to be a lot smaller than these P's. There we go. Alright, let's make it work. And so the way that this hybridization happens is very similar to the last problem actually, where we can promote this s electron here, but then while something else happens, we can promote a p electron. And so what ends up happening, what ends up being the final result, is that we have an electron here and an electron there. And so we erase that electron and we erase this electron. Now what we have here, when it's all, the hybridization is all said and done, is half empty, 2 fulls and 2 half empties, or half fulls if we are optimists in this world. So if we draw out this hybridization, it's sp3d2 and it has six orbitals, and I'm making this one really big to compensate for this teeny one right there. So 1, 2, 3, 4, 5, 6. Okay, so we take the S here. S is half full, P half full, and then PY, PZ full, and then D half full, because as we can see, actually by taking two full orbitals and moving them over into empty orbitals, we are making these ones half full and making these orbitals go from empty to half full. And so this gives us four half-filled orbitals. And this actually works perfectly with this picture, because these four can bond with a fluorine, and use sigma bonds. Okay. And so then this will fill, because these are the fluorine electrons. And then finally, so this represents these bonds. This, and this. And then these two middle P's will represent lone pairs of electrons. Lone pairs of electrons that are also sigma, well, they are in hybrid orbitals, and they would be sigma bonds if they were bonded to other things. So this is exactly what this geometry looks like in this molecule. And when we count the electrons, once we put the lone pairs, we got six lone pairs, 6 electrons in lone pairs around the fluorines. 6 times 4 is 24, plus the 8 electrons bonded, that is 32, plus 2 lone pairs around the xenon, that is a 36. We are good. And what we would call this molecular geometry with 4 bonded pairs and 2 non-bonded pairs around the central xenon atom is a square planar. We can never get rid of this planar word. It is just chasing us around. And so I am definitely out of time by now. Not going to hit 40 minutes. Will not let this happen. So I will see you in the next video, and we will discuss more of this, applying bonding theories in more complex delocalization and other problems in general. So hope you stayed all the way through. You guys are dedicated.